So then, here are some important lessons that we learn from the results of our analysis. So, lessons. The first thing I want you to notice is that the shift itself is relatively small unless the wavelength of the light, the wavelength, and in fact, I want to think about the incoming wavelength, unless the incoming wavelength is also very small. So, let me give an example of this. So here's an example. Say we tried visible light. Visible light. So for visible light, right, the typical wavelength, lambda, would be around, 5 or maybe 6,000 angstroms. So the typical wavelength is about 5,000 angstroms, right? Now, when we look at our Compton formula, you see the new outgoing wavelength will be the incoming wavelength plus this quantity. Now, this quantity has magnitude of lambda naught, 0.02 angstroms, right? And it's that multiplies a number which is always positive. Well, technically it could sometimes be 0, but because cosine is always less than or equal to 1, this will always be a positive number. The very biggest, for example, that this could be is if cosine is minus 1. Then this could get up to a factor of 2. But at typical angles, really, the order of magnitude of this quantity is it's somewhere around 1, really, frankly. So that would mean in visible light, lambda is 5,000 angstroms. The outgoing wavelength, the maximum even, right? If I take that factor to be 2, right? If I do theta equals 180 degrees, complete backward scattering, right? This would become a factor of 2, so I'd have to add 0.04 angstroms. The outgoing wavelength would be 5,000 angstroms, 0.04. Okay, it's a very tiny shift, right? You can count how many decimal places, 1, 2, 3, 4, 5. This is about 1 part in 10 to the 5th. So that also means the frequency shift will also be on that order, a tiny shift of about 1 part in 10 to the 5. So if I were doing this experiment with visible light, let's take a look at our experimental output. This new prime, right, is going to be shifted over by such a tiny fraction compared to the main peak here. I would just have these two peaks basically on top of each other, right? I could have one peak like this, maybe. The other peak is centered almost at exactly the same spot. And if you add those together, it's just going to look like one big peak. You are never going to resolve the fact that anything is going on. So it's entirely reasonable that such effects had never really been noticed before. And you'll note other types of electromagnetic waves, like radio waves, have even far lower frequencies than visible light, and therefore much longer wavelengths. And so this 0.02 is going to look even tinier for those. So you're not going to notice it at all. That's why it had not been seen. That explains that. Now, if you want to begin to notice this, you could try some higher frequency waves. Maybe X-rays you might think about. So maybe X-rays. But for X-rays, the lambda for an X-ray is on the order of the interatomic spacing. That's why people use X-rays actually to probe crystal structure. So those wavelengths are maybe 1, 2, 3, 4 angstroms. Just to make our lives easy, let's pick 4 angstroms. That's kind of on the long side, but not too unreasonable. Then again, lambda prime max, the maximum we could get for the scattering for the outgoing waves would be, again, we're going to be adding twice this lambda naught, because remember, the maximum the cosine can be is minus 1. The maximum this factor is when cosine is minus 1 is a factor of 2. So that would add a 0.04 to the 4 angstroms. That would only be a 1% shift in the wavelength. Okay? And even that you may or may not see, right? It's really going to be a tiny shift. And in these experiments, these peaks aren't necessarily super sharp. And if I have this peak shifted over again by just like 1% over, I'm probably just going to see it as one big peak that looks more or less centered where it's supposed to be. So even X-rays aren't going to matter very much. We really need gamma rays where the wavelength is even shorter, when lambda maybe is getting down to around, sure, 0.04 would be a great one, right? But we need something that's at least 10 or 100 times shorter than your typical X-rays, because then you'll see the new wavelength will be like 0.44 angstroms. And at that point, okay, right? At that point, it's a 10% change going from 0.4 to 0.44. You might be able to begin to resolve this. So this helps explain why this effect would not have been noticed before. The second thing I'd like you to notice is that the effect actually vanishes as m, the mass, I should write lowercase m here, as m gets large, right? And that's very good because that brings us to our correspondence principle, right? Which is in classical physics, as we described, this effect shouldn't be there. We really should have only frequency nu naught coming out in classical physics. But what I'd like you to notice is that this Compton wavelength, here's my formula for it, right? When the mass of the particle is large, not some tiny electron mass, but if the mass is much larger than the electron mass, then this shift is going to be very, very tiny, right? And the larger I make my mass, the smaller and smaller this shift is until it's essentially completely negligible. And then I reach correspondence with the classical physics result. So that is good. That's an important check mark that we would want to have. Now, formally speaking, you can also do this analysis by doing what's called the classical limit. And I just want to show you how this works, right? If I take the limit of this shift as formally, mathematically, as h goes to 0, remember lambda naught equals h over mc. Of course, as h goes to 0, that is going to be that result then is going to give me that lambda naught will actually approach 0 in that limit. And as you can see, that's again what we would expect in classical physics, and making this h go to 0 is very much like saying, okay, let's put a macroscopic mass there, like someone in a classical physics experiment would be working with, and that would just be so much easier than what we're talking about here. The fact would not have been noticed in ordinary experiments, and so we can really explain all of the previous physics. Now, here's a third interesting point I'd like you to think about, which is, okay, fine. It seems like we've got a great understanding here of what's going on in the experiment. We can predict very accurately that there's going to be scattering at this new frequency. But the experiments themselves still show scattering at the expected classical frequency. So we might want to ask ourselves, well, why does that happen? Why or how? Why do we still see the original frequency, nu? Or in my diagram up there, I was calling it, nu naught. Remember, we had dropped the naught subscript. Why do we see nu naught still in the experiments? And the answer to this is kind of already embedded in our analysis, right? If you go to the original experiment, we are scattering things off of this target, right? And as we said, these electromagnetic waves with their electric fields interact with these negatively charged electrons in here and create this scattered wave, right? But also remember, there aren't just charged electrons in here to interact with the light. There are charged nuclei. And the nuclei, as you will recall, are always at least 1,800 or even more times heavier than the electron. Well, that's because we've got nuclei, right? And for nuclei, then M is at least, right, for the lightest nucleus, 1,800 times larger. And if it's 1,800 times larger, or about 2,000 times larger, that implies this Compton shift factor is going to be 2,000 times smaller, right? And that's going to be very small. We're not going to notice that in our gamma ray experiment. If I divide 0.02 by 2,000, it becomes 0.01 divided by 1,000, so I have to add 3 more zeros. It would be that many angstroms, right? And the gamma rays that we are using only maybe go out to 0.01 or something along those lines, right? So even for them, you're still going to see something coming in then as the classical peak. So this is really a beautiful experiment. And the fact that it works so well that we can predict the shift in the peak really confirms the idea that we are transferring exactly as much momentum in our photon packets as we had assumed in our hypothesis. So the final point is that this really confirms the momentum formula for the photon, namely that the momentum for a photon we can take to be always exactly this fixed magnitude h nu over c.